So welcome to the 11th session. They're sitting pretty close by. It's good. So welcome to this session. This session actually is going to be a great one. Very diverse. You're going to learn a lot of very basic, fundamental, interesting topics. We're going to see the first two works is going to be on differential privacy. Then we're going to have a talk on communication and information complexity in the interactive setting. We're going to see a talk on two-prover games. We're going to see one talk on kind of structural complexity and the problem of minimum circuit size problem, which is a very fundamental one. So let me give kind of a very quick overview about these really nice works. So the first one is, as I said, on differential privacy. And differential privacy is really amazing. It's used a lot. Probably, we're all using it now. I think it's already on iPhones, and Google uses it, and so on. It's very widely used idea. And essentially what it does is say, you take data, which is real valued, input, and you apply some function, some real valued function on this data. And you want to do things privately, so you add some noise to it, okay, which from some continuous probability distribution, some Laplace noise. The first observation of that's going to be the first work is actually that this notion, because it's talking about real valued function and real valued data and continuous probability, all this real valued, it's not compatible with computers today, which are discrete. And at first it might seem, yeah, but that's kind of a minor issue, we can easily correct it. It turns out it's not true. It was shown that it's actually a real concern, and it was shown that actually the common implementations of these algorithms are actually insecure and vulnerable to real attacks. And what we're going to see in the first talk is a really interesting way of doing discrete differentially private algorithms that are compatible with our computers. This is going to be really wonderful kind of bridge between doing a fundamental theoretical research and a very applied problem. So this is going to be the topic of the first talk. And the second talk, again on differential privacy, is, sorry, I forgot to say, the first talk is by Balser and Vadan. And the second talk is about differential privacy. And so in general, what we think of differential private algorithms is algorithms that their goal is to estimate statistics on the data. So there's data, and you want to estimate statistics on the data. And the observation in this work, the second talk by Caro and Salil Vadan, is that actually this is not really what we want. We don't want to infer statistics on the data. What we want is some statistics on the underlying population, and which is kind of what we're hoping to get by doing statistics on the data. But since what we want is actually statistics on the underlying population, what you really want is a measure of statistical significance, like we have in common statistics. And this is what this paper does, suggests this measure in the regime of differential privacy, and in addition talks about privacy utility trade-offs. So what's the cost of getting privacy in the differential privacy setting? So this is, again, a very, very nice, innovative way of thinking about differential privacy. I have to say, both these works are very, like perfect ITCS works, very kind of conceptual and innovative, and you'll hear more in the talks. The third, what's this? Okay. Okay, forget about the text. I don't know where that came from. So the third talk we're going to hear about is by Braverman, Ganot, Korlendraz. And this is one of my favorite topics of all times, which is data compression, but in the interactive setting. So what do I mean? So here you have two parties. They each have an input from some distribution, from some joint distribution, and they communicate. And now people ask, how much information is actually revealed by this communication? Okay? They may be talking a lot, but revealing no information. So the question is, can we compress the communication to actually the information complexity, or polynomial in the information complexity? In the non-interactive setting, we know yes. In the interactive setting, this turns out to be a very tricky answer to this question. And actually, there is a previous result by these authors that said, no, you cannot. Okay? This actually made me very, very happy because I like to talk, and I'm very frustrated when people tell me that, I'm giving no information. So now, there's a lower bound, so I feel very happy. However, this lower bound turns out, the lower bound they showed is this lower bound is for interactive protocol where the communication complexity was really, really huge, like a double exponential in the information complexity, and it left open the question, maybe you can do weak compression. So what is weak compression? Weak compression asks, can we compress the protocol? So now you're talking communication complexity, which is a lot, but maybe you can compress it to the information complexity, or polynomial information complexity, times polylog term in the communication complexity. So this was left open. Again, a very, very fundamental question about information versus communication complexity. And again, to my personal happiness, the answer is no, we cannot. So again, feel free to talk, convey no information. You can always point to this lower bound and make yourself feel good. I think my husband will be less happy with this lower bound, but let's continue. Okay, so the fourth talk by Braverman and co. Will be on the information value of a two-prover game. So again, this is again a very, very innovative piece of work, which I really liked. So here, in this setting, we have two players, and they're trying to win a game. They're getting in some queries, U and V from some distribution. They need to give answers, and they're trying to give answers that will satisfy some function, which means winning the game. So there's a lot of work on two-prover games, but usually, or always, I think, or usually I should say, the model is the provers cannot communicate. That's why you have two, okay? They cannot communicate between them. And what this work does is a really, really, they say, you know what? What if we allow them to communicate a bit? A very interesting model. And what they do, they study the trade-off between the information cost and the success probability. So if we allow them to communicate kind of epsilon bits of information, how much does it increase their chance of success? And very interestingly, they show a connection between this trade-off and parallel repetition for two-prover games. And it really sheds light also on previous results, why we don't have strong parallel repetition, and so on. This is a very insightful piece of work that I really enjoyed. And finally, the last talk of the session by Allender, Groucho, Malkovich, Moore, and Morgan is about one of the most fundamental problems in NP, which is the minimum circuit size. Or actually, they talk about two problems, the minimum circuit size problem and the minimum KT problem. So what are these problems? So the problem is the following. It's a compression problem. Given a truth table, okay, is there a circuit of some size, some small size, some bound, that corresponds to this truth table? Or the second one, is there a short program, a program of given size that describes this, this truth table? And these two problems are known, of course, they're in NP. They're one of the most fundamental problems that are kind of intermediate NP problems. So we believe they're not NP complete. We don't think they're NP. It's kind of along the graph isomorphism, factoring problems, kind of these limbo problems that we don't know where they live in. And what this work shows is a reduction. Well, they show a lot of things, actually, but if I have to choose one thing they show is a reduction from a graph isomorphism to these problems. I mean, previously, these are problems that have been studied, and there were reductions. What I find most innovating about this work is that they do it using interactive proofs, and that's a very interesting kind of way. The way they look at this problem is extremely interesting and innovative. So, so without further ado, enjoy the session, and we're going to start with the first talk on differential privacy and finite computers of Victor Balser and Salil Vadan, and Victor is going to give the talk.